Well, happy Friday, everyone, and welcome to GeoHug. But I'm really looking forward to hearing from this week's rockstar, Sam Davies. So, Sam has a diverse background, having trained in the British Army Reserves and studied a master's in psychology. He then returned to the world of geology, moving to WA, working as an exploration geologist. And during that time, he did a PhD at UWA. So this research looked to better understand decision making and risk in mineral exploration. So thank you so much, Sam, for joining us. It is horribly early there, so we're very appreciative to come on to have a chat with us about all your research. So thank you so much.
Cool, thanks, Jess. And thanks everyone for coming along. Yeah, it's pretty early, so I apologize in advance if this isn't the most slick presentation you've seen. It's a bit of a wrap up of the PhD research that I've just finished off, and I'm mostly going to talk around evaluating early stage exploration projects. And what this is the point at which you might be presented with an exploration project, or if you're a large enough company, you might have a few projects in your portfolio, and you're trying to decide whether to allocate resources to go ahead and explore this particular project. And I'm going to particularly focus on the influence that psychology has on this stage of the exploration process, and how it affects the risks that we might take or the decisions we're making during exploration. So just to set the scene a little, it does appear that exploration performance is in decline, and whether this is definitely the case and what might be causing it is probably still open for debate. One theory is that we've essentially already picked the low-hanging fruit, and new discoveries are becoming more difficult, because to make a new discovery, you have to find something that all the previous explorers have missed, using the same tools that they had available to them. And this is probably more likely to be true in the more stable jurisdictions, which are easier to access. The data is supportive that bigger discoveries are often made earlier, and this is likely that their larger footprint makes them the low-hanging fruit that's easier to find. And once these bigger discoveries have been made, the rate of discovery and the size of those discoveries does seem to typically tail off. Okay, I'll just jump back in. So, yeah, so I'll just jump back a little bit so you guys can see the slides. This is where I was saying it seems the exploration performance is declining, and it might just be that we've already had the low-hanging fruit, and we're now trying to make discoveries where we need to find something that previous explorers have missed. That the larger deposits seem to be found earlier, and then the size and the rate of those discoveries seems to tail off, and that these successes seem to come in waves, which people have described as entering new search spaces, and this might be through technological or conceptual advancement. And looking at where we are today, it seems that we're tailing off a wave that really kicked off in about the 80s. And we could describe this as the search spaces that we are currently in are reaching maturity. And what will bring the next wave and how soon it's likely to come is of course, an interesting topic of discussion, but we're not entirely sure. So with that in mind, coming back to the risk side of things, one of the biggest risks that you face in exploration is entering a search space or a project where everything has already been found, or that it's just barren and there's nothing there. And that risk is increased due to this apparent increasing in maturity, and this tailing off within the search spaces that we're currently looking in. And that leaves us either sort of scavenging for what might remain within an excavation, within a search space, or pushing out to try places that don't really have any existing evidence of mineral endowment. So the key question here is there a way that we can predict the mineral endowment of an area before we go in and begin exploring in order to mitigate this risk? So is there a way that we can make predictions around whether there are likely to be any undiscovered projects? And that's the research question that we set out to try and answer and understand. And to help us, we picked a case study. And this was the Sandstone greenstone belt, which is in the Yilgarn Craton in Western Australia. And it's about 1,000 square kilometers, and historically hasn't been a particularly large producer of gold. So total has produced about 1 million ounces. What makes it particularly interesting is most of the gold has come from the weathered oxide zone, and very little has been defined or extracted from the solid bedrock. So very little primary mineralization is known. And also it's received fairly limited exploration since the 80s, and very little academic interest. So the big question here, in comparison to many of the other greenstone belts in Western Australia, is why is there very little bedrock endowment? And there's two possible answers, really. One of them is the mill in the belt was never capable of processing hard rock. So there was really no motivation to go and drill any deeper, because even if you found something, it couldn't necessarily be processed. The other possible explanation, of course, is that there's nothing there. And that's what makes it the compelling case study. So to try to answer whether which of those two it might be, the first approach that we took was I guess a purely data-driven approach, and we tried to use deposit size distributions to see if there were any gaps that might represent undiscovered deposits, and sort of evidence from various places suggests that these deposits follow a log normal distribution, which makes logical sense. From a systems perspective, these ore bodies form through an interaction of various processes that have a multiplicative effect on each other. So if one of those processes doesn't take place, you won't end up with a deposit. Or if one of them only weakly occurs, then the deposit will be very small. Ziff's law is a specific log normal distribution. And we used it, we plotted all of the sandstone belts, and against the Ziff's curve, and we looked for gaps. It's a simple approach, but interesting enough, at least to give you an idea of the maturity of the belt. But one of the issues that we realized with this was, given that most of the deposits were only in the oxide zone, there's the potential that all we're predicting here with oxide deposits is the remaining gold endowment of the oxide zone. So it might not be telling us anything regarding the potential of the bedrock. So to try to get an estimate for the gold endowment of the bedrock, we looked for an analogy, and we picked the Agnew belt, which is to the east of Sandstone in the Kalgoorlie terrain. And we did this based on their geological similarities. But this is a subjective decision, and whether it's correct or not, we're not entirely sure. But what's happened here is, due to the uncertainty that we face and the limited data, we're forced to deviate from a truly data-driven technique into making subjective estimates or subjective decisions. So we then tried a slightly different approach, which is the USGS 3-part assessment. And the first iteration that we tried was to use an outdated grade tonnage model that had been produced in the 80s. And interestingly enough, this perfectly predicted Sandstone's current gold endowment, the known endowment of the belt, and the historical production. So considering the fact that that grade tonnage model was developed from the 80s, before the big second wave of discoveries took place, this aligns really nicely with the fact that sandstones received very little exploration attention since about the same time. So although it did very little to predict what else might be there, it actually predicted what we do know quite well, which was interesting enough in itself. So then the second approach we took was to rerun the model, but to use an up-to-date grade tonnage model based on the deposits within the entire of the Yilgarn. And this gave much more optimistic predictions that there are several million ounces of gold left to be discovered. But the question here is, have we used the correct grade tonnage model? Again, we've had to deviate from a purely data-driven approach to a more subjective decision in terms of choosing a specific grade tonnage model. And so the third approach that we took was, we admitted we can't escape this aspect of subjectivity. So why don't we ask the experts to also simply define the grade tonnage model themselves? So they estimated the grade tonnage model. And to do this, we presented them with every data set that you might expect at this stage of exploration. Maybe more than you'd reasonably expect. And the idea there was that we would simulate sort of a real world example of what might actually happen within a company when they come to review projects and decide whether to continue with them. And out of the 23 expert participants, we got quite a range of estimates from 2 million ounces to almost 17, which is anything from, we've pretty much found everything already and it's not worth exploring here, all the way through to this is one of the most exciting places you're probably exploring at this time. So to take stock, managing the risk, I think it's important to be able to estimate undiscovered mineral endowment. But due to the uncertainty that's inherent in exploration, it seems that this can't be done in a purely data-driven way. However, asking the experts seems to result in a really vast range of estimates. So the next question is why, and what could we do about it? Or who out of this group of experts should we listen to? And to try to help us understand why, we conducted a second study where we presented the same questions and the same data to a group of non-geoscientists as a sort of a control group. And the results here were, they made very conservative estimates, which were similar to about half of the expert geoscientists. And within the metadata that we collected and the discussions that we had afterwards, it seemed that the more conservative geoscientists and the non-geoscientists were basing their estimates more on the known deposits in sandstone. They're saying maybe a few more of the same. And then the more optimistic geoscientists were basing their estimates on more, they were taking more of a conceptual approach and seeing the potential, maybe from a mineral systems perspective, that there could be larger deposits within the bedrock. But you could also ask, is there a risk that they're being overconfident, or is something else at play here? Which brings us on to the discussion around psychology and how that might affect these subjective decisions or estimates, and particularly things like cognitive biases. So we looked for possible explanations to try to understand the variability in the expert estimates, because as interesting a case study as it is, the unfortunate truth is we don't know how much gold is in the belt. So rather than being able to say this group of people were correct, we try to tease it apart and make predictions as to why there may be this variation in estimates. And one of them is, of course, that the study methodology is flawed. It'd be really interesting to see some follow-up studies. And if anyone does want to go ahead and conduct any of those, I'm more than happy to help out as well. In terms of the methodology, we did do various things to try to make sure that it was consistent. We presented exactly the same questions and the same data sets to every participant. And we even deviated from the standard USGS approach in that rather than having a group workshop and looking for a group consensus, we collected individual estimates, which we then aggregated together. And this was to avoid the risk of introducing sort of group-based biases. Another explanation, a possible explanation, is that the data is not relevant to the question that we're asking. I really hope that's not the case. But we've been using the same data sets to review exploration projects for a while. So I'd shelve that as a possible explanation. Another one is that each participant, although they're an expert, they're only a domain expert within a specific area, and it's unlikely that covers all of the areas of expertise necessary for this kind of to answer this kind of a question. The data sets that we presented to them involve geochemistry, geophysics, structural geology, economic geology, and it's unlikely that any one person can be an expert in all of these things. So in terms of coming up with an estimate, we took a bit of a wisdom of the crowds type approach, where we had individual estimates and we aggregated them. And the idea is that the group estimate is better than any one individual because you've essentially combined their expertise. So in terms of individual expertise, hold that thought for now. Another thing that we noticed was that the two most extreme estimates were the two most experienced participants. And generally we collected various metadata during the study. And one of the things we noticed was that with increasing experience, we got increasing variation in estimates, which is really interesting and to a certain extent brings the validity of experience and expertise into question. And so it seems that perhaps there's quite a few biases affecting estimates. And biases seem to be prevalent in what we call low validity tasks. And what these are tasks where there's a lack of consistent feedback, and that doesn't allow learning that then calibrates estimates. And that learning and calibration is what reduces bias. And thinking about it, this could be particularly true for this task and this stage of exploration, where we have quite a low base rate of success, and it's unusual for people to write up failed exploration programs. So in general, we're getting very limited feedback. And without getting into too much detail around psychology and how we learn, which I'm more than happy to discuss during the chat later, the bottom line is that in order to learn effectively, it needs a good feedback loop. And this is potentially missing for this specific task of evaluating exploration projects. And I suppose if you think yourselves, how often would we make these kind of estimates regarding the quality of a project and then go on and explore these projects and find out what the answer actually is, even across an entire career? It's probably not very often. And in this particular case, it seems that these biases could be increasing with experience. And that might be because during a career, because this doesn't happen that often, one person may have a number of positive experiences and successes, and another may have several negative outcomes. And this actually exacerbates their bias. It's like if you only roll the dice a few times and you roll a 6 every time, you'd assume that you always roll 6s. So again, it's the lack of feedback increasing the bias in certain individuals' estimates. So the next question is, well, what can we do to overcome this and to improve our estimates? And can we practice or can we train to become better at doing this? And maybe one option is to develop tools that simulate these real world projects, and they allow us to go through the process of estimating the quality of exploration projects. So you might present the person with real data, they make estimates, and if it's a fairly mature province, you can present them with the answers or the best known answers. And this can provide them with feedback and sort of fast track the learning process and improve their calibration. So in summary, risk is inherent in exploration, and particularly now with this increasing maturity, it's probably ever more likely that you enter a depleted or barren search space. And based on the studies that we've done, it doesn't seem that taking an entirely data-driven approach will necessarily help to resolve this. And that's probably because of the uncertainty inherent in exploration. It just means that there's always an element of subjectivity. And this sort of task is quite complex as well, and it requires a degree of sort of creative thinking, which at this stage is not something that any AI or sort of machine approach is capable of doing. So yeah, until the machines take over, the real question is, what can we do to improve human estimates? So the two key takeaways from our research, I guess, were that a task as complex as this requires a very broad base of experience, more broad than maybe any one person could hope to accumulate. So it's important to build exploration teams with diverse skill sets to cover all of these different domains. But whilst doing that, being careful to avoid introducing group biases. And you can avoid those by doing things like having independent estimations rather than looking for group agreement and sort of peer review processes, that sort of thing. And the other key takeaway for us is that evaluating exploration projects probably represents a low validity task. And in a low validity task, biases seem to be prevalent. But rather than focusing on any one bias, we think the best approach is to potentially develop these practice or training environments where you can promote learning and counter many of these biases through useful and regular feedback that maybe a day-to-day job wouldn't provide. Yeah, so I guess there's a risk if we avoid or ignore these biases, then we might go ahead and not find anything and make poor decisions depending on who we listen to, given the variability of these estimates. So it's probably worth applying a couple of these techniques to improve our ability to make subjective estimates. Cool. Thank you very much. I look forward to questions and discussion. And if you're interested in reading any more, these are the main references, and you can drop me an email or head on to ResearchGate, and I can send you a copy of any of these. Thanks, Jess.
Thank you so much. That was so interesting.